This is Chapter 8, problem number 47. A particle of mass 1.18 kilograms is attached between two identical springs on a horizontal frictionless tabletop. The springs have force constant K, each initially unstressed. If the particle is pulled a distance x along a direction perpendicular to the initial configuration of the springs, as in figure P847, show that the potential energy of the system is U of x is equal to kx squared plus 2kl times L minus the square root of x squared plus L squared. First, we must list our givens. K is the spring constant of each spring. L is the original length of each spring. X is the distance that the particle travels perpendicular to the spring's initial configuration. The springs are identical and originally unstressed. There is no friction. We know that U of x, the potential energy, is equal to work, which is equal to the integral of force, F of c, where c is the change in length of each spring and a function of x. We also know that for a spring, the force exerted on the spring is equal to K, the spring constant, times the change in length of the spring. So F of c is equal to K times delta c. Potential energy is the integral of force. And we know the force for a spring is K times c. So substituting in, we get that the potential energy is the integral of kc dc from 0 to c because it's initially unstressed and changes a length of c. After integrating this, we end up here, which is in fact our work equation for springs, telling us how much work it takes to stretch a spring a certain distance. Now, this applies to only one spring, but since both springs are identical, both are initially unstressed, and because the particle is moved perpendicular to both, we know that the total potential energy is double this. So the total potential energy is equal to kc squared. Remember that c is a function of x, so now we need to find c in terms of x and plug that into this equation. We know that c is the change in length of the spring, which means it's the new length of the spring subtracted by the old length of the spring. To find the new length of the spring, we know the old length of the spring is L, but we still need to find the new length. So looking at this diagram up here, we can see that there is a mass stretched a distance x perpendicular to the springs, and they were moved from their original position L. So we need to find the new length of the springs after it's been stretched, which is where the question mark is. So what we need to do is use the Pythagorean theorem. Using the Pythagorean theorem, we get x squared plus L squared is equal to new length squared. Then we take the square root of both sides to get that the new length is equal to the square root of x squared plus L squared. We only use the positive length because there is no negative length. So now we have found the new length, the hypotenuse, to be the square root of x squared plus L squared. So now we can find c, the change in the length of the spring. New length minus old length. New length is the square root of x squared plus L squared, and the old length is L. So c, the change in length of the spring, is equal to the square root of x squared plus L squared minus L. Now that we have found c, we can substitute it into our equation. Doing so, we find that U of x is equal to k times the square root of x squared plus L squared minus L, quantity squared. Then we do algebra and square the term. Doing so, we get that U of x is equal to k times x squared plus L squared minus 2L times the square root of x squared plus L squared plus L squared. Then we simplify the brackets by combining like terms. Doing so, we get k times x squared plus 2l squared minus 2l times the square root of x squared plus l squared. Then we distribute k into the parentheses to get u of x is equal to kx squared plus 2kl squared minus 2kl times the square root of x squared plus l squared. Then we factor out 2kl out of the last two terms, and we end up with kx squared plus 2kl times l minus the square root of x squared plus l squared, which is our final answer. U of x is equal to kx squared plus 2kl times l minus the square root of x squared plus l squared, which is what we were told to derive. B. Make a plot of u of x versus x and identify all equilibrium points. Assume that L is equal to 1.20 meters and K is equal to 40.0 newtons per meter. First, our givens. We have the potential energy equation we derived in part A. U of x is equal to kx squared plus 2kl times L minus the square root of x squared plus L squared. We're given that L is equal to 1.20 meters and that K is equal to 40.0 newtons per meter. Now we plug in those values into our equation and simplify to get u of x, the potential energy, is equal to 40.0 x squared plus 96 times 1.20 minus the square root of x squared plus 1.44. Next, we plug in various values for x and calculate the potential energy at those points and plot a potential energy versus x graph. Every negative x value is equal to its positive value because x is squared, creating a parabola-shaped graph. The points of equilibrium are where the net force in the system is equal to 0. Since the vertical component of the force is always 0, we will only look at the horizontal component, F sub x. There is only one moment where the horizontal component, F sub x, is equal to 0, and that is when x is equal to 0, when both springs are initially unstressed. C. If the particle is pulled 0.500 meters to the right and then released, what is its speed when it reaches the equilibrium point x equals 0? First, we list our givens. We know that a particle of mass 1.18 kilograms was pulled 0.500 meters to the right, which is why it's positive. We also know our potential energy equation from part B, and we know that we're trying to find the speed when the particle reaches x equals 0, that's the equilibrium point, after being released. We also know that the tabletop is frictionless. We must obey the law of conservation of energy. So we know that the initial kinetic energy plus the initial potential energy plus any change in mechanical energy is equal to the final kinetic energy plus the final potential energy. So we know the initial kinetic energy must be 0 because the particle is standing still. You need motion to have kinetic energy. We know that the change in mechanical energy is also 0 because there's no friction. If there was friction, then some of the mechanical energy would be turned into internal energy, or heat. But since there's no friction, the mechanical energy remains potential or kinetic. So the change is 0. We know the final kinetic energy is equal to 1/2 the mass times the final velocity of the particle squared, and that the final potential energy, since the particle is at the equilibrium point, is 0. we're trying to find the final velocity when x is equal to 0. So we rearrange the equation to solve for v. Final velocity squared is equal to 2 times the initial potential energy divided by the mass. So the final velocity is equal to plus or minus the square root of 2 times the potential energy initial divided by the mass. We can find the initial potential energy easily by merely plugging in 0.500 meters into the potential energy equation. So U of 0.500 meters is equal to 0.400 joules. Plugging that in, we get that the final velocity is equal to negative times the negative square root of 2 times 0.400 over 1.18. It's a negative sign because the velocity of the particle will be to the left since we pulled it to the right initially. So it's going to move to the left, giving it a negative velocity. Solving for that, we get that the velocity is equal to, negative 0.823 meters per second.